Hello and welcome to this video where today we're going to be looking at particles and antiparticles. But before we do so, we need to have a quick look at some of the units that we measure energy and mass with when we're talking about very small particles. Now, in order to do this, we need to go back to something that Einstein said. And Einstein said that both energy and mass, when we're talking about small particles, are interchangeable. In other words, energy and mass really are the same thing. And if we've got energy, we can convert it into mass. And if we've got some mass, we can convert it into energy. And this is summed up in his very famous equation, where he said that energy is equal to mass times the speed of light squared. In other words, if we have some mass in kilograms, we can calculate how much energy would be released if all of that mass was converted into energy. So this is his equation, and as we know, energy is measured in joules. So that's this one here. So energy is measured in joules. Our mass is going to be measured in kilograms, and c squared is the velocity. So velocity is measured in meters per second, but because we've squared it, we've got meters squared per second squared. But we know that the speed of light, if you look on your data sheet for your exam, is simply 3 times 10 to the 8 meters per second. Okay, so if we want to work out the energy of a certain mass, we would take its mass in kilograms and multiply it by this number squared. So let's do a quick example. I want to work out the rest energy of this proton. Well, the mass in kilograms is given up here. So we do what we do with every calculation. First of all, we write down our equation. So we write down Einstein's equation, and then we just put our numbers in. So the mass is the mass that's up here, which is our 1.67 times 10 to the power of minus 27 kilograms. And then we simply multiply it by the speed of light squared. So the speed of light is 3 times 10 to the 8. And then we square it like that. And if we do this on our calculator, we end up with an energy of 1.503 times 10 to the power of minus 10 joules, because energy is measured in joules. So that would be our answer. Now, that's fairly straightforward, apart from we always end up with energies that are really small, so like 10 to the minus 10, that sort of thing. So we often use different units, and we use units, instead of using joules to measure the unit of energy, we use something else. We use this electron volt. Now, often in an exam you're asked for the definition of an electron volt, and it's this here. Basically, the electron volt is the work done. And if you remember back to your GCSE physics, then work done is measured in joules. So really we're talking about an energy, and it's the amount of energy that's needed to accelerate just one electron through a potential difference of 1 volt. Now, it doesn't really matter what that means, but what is important is that this is just a different unit of energy, okay? And it's a very small unit of energy, so 1 electron volt is simply given by 1.6 times 10 to the minus 19 joules. Okay, so if we have a number in joules, what we need to do, so if we want to convert from, for example, from joules, and we want to go to electron volts, then what we would do is we would divide by this number. So we would always divide by 1.6 times 10 to the minus 19. Okay, if we want to go the other way, if we want to go from electron volts to joules, then we simply multiply by 1.6 times 10 to the minus 19. So what we could do is we could go back and we could now convert our proton mass, our proton energy that we worked out before, and we could convert that into electron volts. So before we saw that our proton, the energy of our proton, proton energy, we found was equal to 1.503 times 10 to the power of minus 10 joules. But I don't want it in joules, I now want it in electron volts. So I'm converting from joules to electron volts, so I have to divide by this number. So if I divide now by my 1.6 times 10 to the power minus 19, I end up with this number. I end up with 939 375,000. So now instead of having really small numbers, I've got a really big number. So often what we do is we now write these energies as, instead of in electron volts, we write them as MeV. And if you remember, the M simply means 10 to the power 6. So this is just the equivalent of, if we do it to three significant figures, 939 MeV, or 939 mega electron volts. Now this might seem like a lot of effort, but later on when we come to have a look at particles and antiparticles, it actually makes life a lot easier. So let's do a little question. You might want to pause the video now, because what I'm asking you to do is calculate the rest energy in MeV of the electron, and the mass in kilograms is given here. So if we want to do this, the very first thing is we start off with Einstein's equation, so E equals mc squared. We put our numbers in, so our mass of an electron is 9.11 times 10 to the power of minus 31 kilograms, and again we multiply it by the speed of light squared, so 3 times 10 to the power of 8 all squared, and if we do that we end up with an answer of 8.199 times 10 to the power of minus 14 joules. Okay, but I don't want joules, I want mega electron volts, I want MeV. So what I'm going to do is I need to convert these into electron volts. So 8.199 times 10 to the minus 14, and then I divide it by my charge of 1 electron, so 1.6 times 10 to the minus 19, and if I do that I end up with a huge number, but so 1512 437,500 electron volts, but that's still no good because I want this in MeV, so I basically have to divide this by 10 to the 6, so I end up with an answer of 512 MeV. There we go. So if I was to convert all of the mass of an electron into energy, then I'd be able to get out 8.199 times 10 to the minus 14 joules, which is equivalent to 512 MeV. So that's the end of the units. What we really want to do is we want to talk about these particles and antiparticles. Now, a long time ago, back in the 1920s, a physicist called Paul Dirac theorized, he came up with an idea that every particle has a corresponding antiparticle to it. It's a little bit like a particle looking in the mirror. Now the important thing about about any particle is that the particle and the antiparticle have the same mass. That's really, really important. And when we say the same mass, they have exactly equal mass. But everything else is opposite. So here's our proton. Proton, the symbol's P. The charge, as we know, is plus 1.6 times 10 to the minus 19 coulombs. So the corresponding antiparticle is called the antiproton. The symbol for an antiproton is just the same as the symbol for a proton, which is a P, but we put a bar over the top. But everything else is opposite. So instead of a proton being positive, the antiproton is negative. There's a corresponding neutron and antineutron. Again, the mass of the neutron and the antineutron are the same, but the charges are opposite. But because the neutron is neutral, the opposite of zero is still zero. The electron also has an antiparticle. You'd have thought it would be called the anti-electron, but it's not. It was given a special name because it was discovered quite early. And it's actually called a positron. It's still got exactly the same mass, but it's got exactly opposite charge. So instead of it having a negative charge like this, it has a positive charge like that. Now the interesting thing about these things is actually what they do when they meet. So when they meet, here we've got a proton and an antiproton, and they're moving towards each other. So this one's moving this way and this one's moving this way, and when they meet they annihilate each other in a process called annihilation. Basically all of the mass that's here, all the mass is converted into energy. Okay, now we know that the mass of a proton we can look up on our data sheet, but now this is where our MeV calculations come in. So if you look on your data sheet using more accurate numbers, the rest energy of a proton is that, and because the mass is the same of an antiproton, the rest energy of an antiproton is exactly the same. So we know how much energy is contained in this antiproton and how much energy is contained in this proton. So we know the total amount of energy altogether. So when they collide, they annihilate each other completely, So the total amount of energy is just 938 MeV, add another 938 MeV. Now when they annihilate, because all of this is converted to energy, as we saw before, energy is basically a photon. So all of this mass is converted into energy in the form of photons, and actually it's converted into the energy in the form of 2 photons, and this is really, really important. So we end up with 2 photons, and if you want to know why this happens, it's so momentum is conserved, so that the momentum that we started off beforehand is equal to the momentum afterwards. Now we know that the rest energy of the proton is this, the rest energy of the antiproton is this, so the total energy we've got is twice that, but we have 2 photons. So on average, the energy of this photon is going to be 938 MeV, and the energy of this photon here is also going to be 938 MeV. So what we can really say is that the energy of this proton is converted into this photon here, and the energy of the antiproton is converted into this photon here. Now, that's what happens if these things meet. Exactly the opposite thing can happen. So because here what we've got is we've got mass changing into energy. We can have the corresponding thing happen where we have energy changing into mass, provided we've got enough energy. So a photon can come along, and if it's often happens near the nucleus of an atom. So if a photon comes along, it can spontaneously change into the proton and an antiproton, and it must change into a particle and an antiparticle, but it can only do this if it's got enough energy. So we know that the rest energy of this again is 938 MeV, and the rest energy of this is 938 MeV. So the energy of this photon must be at least 938 MeV and another 938 MeV. So my energy of my photon must be 938 times 2. And we can do that on our calculator. So the energy of this photon we must have enough energy to make the rest energy of the proton and also the antiproton. What's kind of interesting is if this photon has got more than this energy. If it's got more energy than this, what can happen is that it makes a proton with this amount of energy, it makes an antiphoton with this amount of energy, and any extra energy, so anything that's extra, any energy that's left over, is given as kinetic energy. In other words, it actually gives these things some energy to move away from each other. So that's basically it for particles and antiparticles. What we've done is we've covered the conversion of kilograms into an energy using Einstein's equation, and then what we did is we then converted joules into mega electron volts, which are very useful at this level. And then we've just had a very quick look at particles and antiparticles, but the important things are that when particles and antiparticles meet, they annihilate, so all of the mass is converted into energy in the form of 2 photons, and occasionally a photon, which is just a lot of energy, provided it's got enough energy, can be converted into mass, so it can be converted into a particle and also an antiparticle. So that's it from me. I will see you again soon.